few things on the table. Pulse motor mayhem. Please like, subscribe, and hit the notification bell. Hey, what's up? How's it going? All right, so what I'm going to start off by doing is connecting the power, which is this 12-volt battery over here. All right, so this is the most efficient way to run it, power cost-wise. We'll give it a minute here. All right. Okay, so I just made the connection to the ground shorter and the performance increases, but the cost in amps goes up as well, so the efficiency goes down. But this is a happy medium right here. The motor's going fast and the amp cost isn't too high. This is where you want to be right here for efficiency. And if we turn on overdrive, it goes up about 200 more milliamps to about 900. But as you can see, it ekes out a little bit more performance than the previous version, but it's not more efficient. Performance and efficiency. I think some people get these, I got it confused, at least for the first little while I was, thinking about it. I mean, and there is like a happy equilibrium for performance and efficiency. So this is with all this connected to ground. That's what this is. There's 5 coils here, 2 in this one, and then each one of these are single file. And as you can see, very slow, but it costs about 60 milliamps to run this. Can you, if you can't hear me, let me know. I'll hook up a mic. But basically, with all this wire connected, and each coil is connected via diode, rectifier diode. So it's all going in one direction. So you got to spin it in that direction, basically. Yeah, let's turn on, this is the most efficient way to run this motor, I think, right here. So this costs about 600, 700 milliamps. It's 12 volts across the board. So it's 12 volts, and then the milliamps is all that's changing. So I think this way right here would be good, and that's these 2 coils and this coil. Alright, so I'm going to start over and explain from the top what's exactly going on here. Okay, we got one power input right here. Let me make sure you can see what I'm doing. Yeah, one power input right here. And we got 3 ground connections to the common ground. Okay? Now when you put the same amount of power through a lot longer wire, you're going to get less output mechanically, but you're going to get a lower cost as well in ampage. So this is with the ground right here. So it's connected via this one, everything's connected. Then I'm going to change it by using the path of least resistance to a shorter path, which is right here. And it connects this one, it'll cut these 2 coils out of the equation. And then I have a third one, which will cut this one out. And it's cool how I can just like terminate stuff by turning on a switch. That's different. So that's just this coil right here. Turn that one off. And then we're working with this one. Turn this one off, we're working with the whole thing. But, you know, with working with the whole thing, you could probably put, you know, 30 or 40 volts in and you'll be all right. Even using a transistor, you put in 31 volts, you're fine. Now, another way that I like to, you know, do this is with a mechanical homemade switch, like so. You got a paper clip on the top. It's real stiff. You want your bounce there to be real small, so you want something real stiff. And then as the magnets pass, it'll bounce it up and off, and you get your switch. You get a little bit of a, what do you call it? An arcing, but it's not green. It's not a green arc. So it's not the copper burning. It's, you know, it's a different arc. And I might hook that up later, just so we can play with it. All right, now this, I wanna spin this to get you to see that the bottom part will start to counter rotate without me touching it. All right, so. Unless it gets stuck on something. But I don't think it will. See what I mean? That wants to do that. It's born to do that. You just have to make it so it's able to do that, and it will. That's uber, man. That's super. This thing is dope. I'm glad I made it.
We've been live for 10 minutes.
Yeah, I'm looking for. There it is.
10
I'm gonna
minutes.
hook up the mic. Hook up the mic. Yeah. Alright, so I think you guys might have a little bit of trouble hearing me, so I'm going to hook up my mic real quick. There we go. Don't know exactly where to put it though. Probably on the table eventually. All right. So yeah, man, I'm proud of this thing. I mean, even though it's only half working right now, it's something else. Does it all by itself, really. You just gotta give it a little nudge. Oh yeah. All right. So, any more questions? Please try to be as specific as possible with your questions. I mean, the more less specific you are, the less specific the answer is going to be. Anyway, I love this design that I got here. As a matter of fact, I'm going to turn it all off. I'm going to show you my new rotor. Now this doesn't go as fast, but it's the smoothest one I've got, and I'll show you why. These magnets are firm in there now because I got iron infused PLA on the bottom part of it, sucking them in there, so it makes less noise and it moves smoother than any of the other rotors that I've made so far. And on 12 volts, I think this is a pretty good design. It's 5.5 inches in diameter. I was originally designing it to have a movable shaft, so it would spin with the shaft instead of on the shaft. But the hole was like 0.5 millimeter too small. So I got to buy more filament to make the next one. All right. But here, I want to demonstrate this again. So we'll give it a spin. And since there's diodes on here, it'll only spin one way. So you have to spin the top in a counterclockwise direction. Now you can either give the bottom a nudge or you can let it do it itself like it's doing right now. It'll get up there. Now I've heard a debate. It's a debate to me because half the people say that it'll speed up counter rotating and the other half say that it'll slow down. And so far, this one stabilizes at 1,000 RPMs. So I don't know about either one. Let's see what this is real quick, though. Almost to 1,000 now. Now this, I believe the pole will stop shaking if it continues to increase in speed. 2951. And you got to divide by 3 because there's 3 magnets. So we're at almost at 1,000. Yeah. So that's pretty cool. And I mean, it's only got 1 drive hookup. It's a 2 drive system. So I'm pretty sure we can get it going faster than it's going right now. But I got to find a way to stabilize that other drive because it's eating up my transistors. It's a 32 gauge drive, I'm pretty sure. That you shouldn't be doing that. Maybe I got them backwards, and this is the 32 right here, and the 20 is the other one. That's awesome, man. I can't get enough of that. It's a 24 volt system, so to only get 1,000 RPMs on 24 volts is not good, but I like it anyway. All right, so again, here we are. I call this the 3 ground system. You got 3 ground connections to the ground. You got 1 power input, and all these are connected in series with the cutoffs in certain places along the way. So you got your 3 grounds, and they're hooked to toggle switches. So I can turn the path of least resistance on and off. Right now, it's the whole thing is the path of least resistance. I'll flip this one. You can hear that. And it changes to this point right here. So these 2 coils get cut out. Path of least resistance says right here. And that's going to be your best one. I got another one here it'll cut this coil out. But this costs almost twice as much as that one did. And it's not going that much faster. So it's the least efficient. There's about 900 milliamps coming out of this thing right now. So we cut that one off. This is about 600 right now. And this is about 60. In between 160 milliamps. And that's awesome. And it's like introverted. So it's like backwards, but with a forward result. So it's like you turn, it's weird in my mind because you're messing with the grounds. So it's like the opposite. Well, I don't know. Maybe it's right. You turn it off and it gets slower. You turn it on, it gets faster, but you're cutting, you're eliminating to make it go faster. That's probably what it's all about right there. And then not only does it go faster, but it costs more. That's the thing right there. So you want to find like a medium. This costs a lot. This is right. This costs a medium amount. This you get like a decent speed out of it. Let's find out exactly how fast it's going. 1,000 RPMs? No, a little bit more. It's stable though. Yeah, it's really stable at about 4,700 divided by 4. So about 1,200 RPMs, let's say. Heck yeah. And then we'll turn on the least efficient way of doing it with the highest speed. And we'll back out the coils. Oh, you hear that? Hell yeah. Oh my God. Woohoo! So we get that less friction from the copper, but we still get it. It's still functioning, right? Oh yeah, that's slowing down. Here, let's move this in a little bit. So we're only running on these two coils right now. Yeah, it's stable. It's really stable. Right around 5,800 divided by 4. I don't know. I'm not doing that right now. It's about 1,300, I want to say. Maybe 1,500. Anyway, not too fast. Not too fast, not too slow. Oh yeah, this one's in there too. Let's move this one up in there too. All right, let's get another reading. And do we slow it down by moving that in or speed it up? Slowed it down. Okay, let's back it out. There we go. That's it right there. Let's see if I put a tinfoil strip on there. Yeah, 1446. I forgot that I did that. All right, sweet. We're going around 1,500, like I said, 1446. Yes. That's not fast. That is not fast, but this is good, man. This is stable. It's not like continuously increasing in speed like most of my stuff does. But I am using a 1-2-3 circuit. So you got 1 for the base, 2 for the collector, and 3 for the emitter. That's connections. You got 1 for the trigger, 1 for the power, 1 for the coil, 1 for the trigger ground, and then 2 for the light that you got to have bridging the collector and the emitter. If it's got to go through a light, it'll work. You can't just clip them together. That won't work. Now, if I get more toggle switches, there's a lot more that I can do here because there's only 2 switches and there's 5 coils. So, yeah, I only have 2 switches. Unfortunately, can't find any of my other ones. But it's enough to demonstrate, the path of least resistance. And then you got to have this one on all the time because it's got the trigger on it. There's only one trigger here. So about 1,300 without the auto drive on or the big drive on. Middle drive is about 1,300. So that's 200 less RPMs for literally about half an amp in cost. So, I mean, it doesn't even compare, really. Yeah, that's 1291. Yeah, we're about 1,300. The other one was 1,500. And then back the copper out a little bit, not so it doesn't like, you want it to be in close enough so that it affects, but you don't want it to be close enough that it drags the rotor down. $777. 748. All right. See what that did. We moved them in real close. Oh, closer. $637. Yeah, it's gonna keep slowing down like that. So about, well, let's leave it alone and let's see what it slows down to. 613. Boop, 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 boop. Give the frickin' pulse motor a little twist. Hello, everybody. What's up? 605. So we're slowing down very slowly, but we are definitely slowing down. That's a counter-rotating pulse motor. All I did was put the stator on a disc that could spin, and voila, it does it on its own. Look at that. You do. I think you do have to put the diodes in there for it to do it like that, but yeah, it does it on its own. Yeah, counter-rotating pulse motor. Awesome. Stabilizing at 600 RPMs over here with the full Monty on here. So let me explain it. We got an 18 gauge coil going into a 20 gauge coil, going into a 16 gauge coil, going into another 20 gauge coil, going into a 16 gauge coil, going into the ground. All connected with rectifier diodes, all pointing towards the ground in the order that I mentioned. All these coils were wound the same direction, clockwise. All these are clockwise coils. And the reason that they're clockwise is that my auto wrapper, when you run it clockwise, I gotta change the shaft. I gotta twist the shaft around because it's a threaded shaft. And when you run it counterclockwise, everything loosens up. So I gotta change the shaft. I gotta just flip the shaft, and then when I run it counterclockwise, everything will tighten up. But these are all clockwise. So they're all hooked and going in the same direction. They're all doing the same thing. And that's the only way it will work, really. Because if you do it the other way, if you got them confused and stuff, when you put the diode into a confused one, it's going to cancel out the effects of the ones next to it. That's awesome. And I feel like I'm so intoxicated by it because I built it and it works. And I did it overnight. I'm like, this is how it's got to be, and then I did it and it worked. So boom, I was happy about that. So you know, it's one of those eureka moments. But you know, there's people out there that are dissing on this, I think, saying that since you can't read off of it, or it does generate electricity. You just don't know how much. Because you can't put a meter on this. There's no commutator. I might make a commutator plate just for a meter, just so we can connect the meter and read off of it. Because I think that would be beneficial. Like, is there any benefit to running a counter rotator? So I'll make this is what I'll do. I'm going to make the commutator plate like so. This is another counter rotator. I'm going to make the commutator plate for the multimeter instead of for the power. And I think we can get some readings off of it then. Probably will slow it down a little bit. That's all right. So we'll go full blast. We're going to cut all this out. This coil, and this coil. We're turning those off right now. Let's see what happens. So now only the 2 coils in here are on and connected. It's all by the path of least resistance. I don't have to do anything else except flip that switch. And it's all, man, it's satisfying as hell to like make something that you can actually like stepper, like a step. You can step it up, step it down, and it's easy. So cool. See, I think some of the differences between me and maybe the similarities, it might not be even differences, but we don't do our homework. We just do it. And if it's safe to do, we just do it. I mean, if it's not safe, read up, man. Read up, do your homework, get your rubber gloves or whatever the hell else you need, because you don't want to have an accident with electricity. I like to stay like in the 12 volt, 24 volt range, at least until I have more know-how of what I'm doing. I mean, I don't want to just accidentally touch something and, that's it. But with a battery of 12 volt size, this is the max speed we get from all these being connected. The real drain on the whole thing is this 1500 turn 20 gauge coil. And it's made out of iron infused PLA, so there's a drag on that too. But I don't know. I think this is smooth. This is the smoothest rotor I have ever built. It's got iron infused PLA on the bottom, so it holds the magnets in place. And then it's just finished up with some carbon fiber. But like any sound you're hearing coming from this is coming from the bearings.
being slightly, and I mean slight, there's no way you're putting a bushing in there or anything. It's just slightly, bearings are bigger than the shaft. But all my other rotors, they like hum, they zing, and that's because the magnets are not held in place. They're just kind of chilling there in their slots. But this is smart. I finished off my iron infused PLA roll to build the bottom half. I knew it would end up like that with a multicolor rotor. And yeah, I just used my carbon fiber PLA to finish it up. And it's toroidal, because I use a toroid in it, but it's definitely connected to the center with two 4 spokes. We'll just stop it real quick. I'll take it off of there. I'll take this off too. I want to show you guys what's underneath there. Now, there's 3 batteries, but only 2 of them are hooked up. There's 3 wedge-shaped coils, 20 gauge and 32 gauge bifilers wound in parallel. They aren't twisted. You can see that plainly. But they are bifilar in parallel. If you think about a line, like a straight line, a single file line, single file coil. Right here, 1 strand wound all the way through. That's a single file. I mean, military, think, single file. School, you're in a line, a single file line. Bifilar, parallel. 2 lines next to each other. Awesome. And then that's what gives it its like power. You can see right here, maybe there's 2 resistors. That's for the input and the output of the transistor. I might change that output one because I want it to run a little bit smoother. Well, not smoother, but like I want it to transcend where it is right now. Now there's a room here for another transistor, but I'm not sure. I want to put that resistor on this circuit over here because it keeps burning out the transistors. And I don't have any more transistors to spend. So the next one I put in there has got to work. And then there'll be 2 drives driving this thing, and it'll go even faster with more torque. Because that's a parallel circuit of 32 and 20 gauge. This is a trigger coil. Now, I think it might be better if I put it over here. Might have a much better response considering the way I have to spin it. I don't know. Maybe it's in the right spot. Maybe this one is done. I don't know. I want to get that second circuit to work. Voila, man, I love it. I can't say enough good stuff about how easy, if you just let it happen, it'll happen on its own. You just have to connect it so you know it'll run, and then it'll do it on its own. Now, as for the stipulations and rules that everybody has about these things, say build your first one and then decide what the rules are. So I've heard that it goes slower. I've heard that it goes faster. I've heard, everything under the sun, it's destructive. There's no purpose. All this stuff, man. I mean, seriously, I appreciate your opinions. I think there is a great purpose for it. It might not be perfectly understood yet, but counter rotation, I believe, is the key to unlocking lots of things, like stronger eddy currents, for example. If you're trying to run something on eddy currents, you want a counter rotation of magnets on one end and aluminum on the other. And you want to twist them in the opposite direction. And if you've tried to do this before, you'll understand that that is not an easy task. So a lot of them go the same way and just spin slower than the one on top or the one on the. This is how I do it. You want to hold that bottom disc with all the magnets on it stationary, and you want to spin the aluminum disc. That's the best way to generate eddy currents. You can hold the aluminum disc steady and spin the magnets. That's how I do it because it's easier. But you want to have one of those discs being stationary because the magnetism or whatever it is, because when I move the copper close to the rotor, it slows it down. When I move an aluminum coil, it slows it down even more. And as you generate lots of current, lots of eddy currents are being generated during the period where they're least synced. I mean, if they're both going to be moving when they're the least moving on one end and most moving on the other, you get your most eddy currents. And man, I've seen this. It's amazing. I want to get into that, but it's totally different than this. It is a totally different learning curve. It's totally different. It's using DC motors that I don't have any idea how they work or something. I don't know exactly how it works, but it looks cool. It's all hell, man. Looks awesome. And I want to kind of run my rotor like that because that looks like the one of the better ways to do it, especially with aluminum. See, if I can get the aluminum disc to spin and have the magnets be stationary, then I'm winning. That's where it's at. You can get some eddy currents doing it the other way, spinning the magnets and keeping the aluminum disc stationary, but it's not as good. Just same as the Faraday disc, generating the electricity by cranking the center disc through the two magnets north and south, like so, is going to get you more energy than spinning those magnets around and holding the disc steady. It should be the same, but it's not the same. And I think it's because the way you spin the disc, you get a lot more torque. And believe me, torque is very important when you want to spin a disc against aluminum that has magnets in it. Torque is important. I think it's awesome though. To think about it, how much torque you get from cranking something is a lot. You got a lot of torque in your arm. I don't think this motor right here has any like real torque to it. That's not really. I mean, that might be able to, wrap up some twine if it was really loose. But yeah, to achieve great amount of eddy currents, I wouldn't use a pulse motor. I would use a lathe motor, some kind of other version of DC motor. I would also have a shaft that could spin. I wouldn't have a fixed shaft. I would definitely have a shaft that I could put something on it and it would move. That's the kind of shaft I need to do something like that. I don't know. I made shafts like that. I forget when I started like making the shaft all stable and stuff. I kind of like it both ways, but yeah, I mean, if you got a nice hole and a good maglev, that's the way to go. Hooking the shaft directly to the rotor. But you know, since I don't have it, I've been looking for magnetic bearings on Amazon. I haven't been able to find one that's suitable for what I'm doing. I haven't even been able to find one. Am I using the wrong? See, this is what I'm saying. They say magnetic bearing, but what is it really called? You know, what is it really called? Then I'll look it up. I'll buy myself one, and we can move on. I've seen like the couplers. Where is it? Yeah. In order to attach it to the shaft, I'm just going to use one of these. Screw it right into the rotor, and then clamp it down with one of these nuts and a wrench. Heck yeah. All right, so let's soup this up. Right now, all the coils are connected to the ground. We're going to cut these two coils out of the equation by flipping this switch. Look at that. Drastic performance increase, but the cost increased by 10 times. There's now 600 milliamps being drawn. With all four coils connected, there were 60 milliamps being drawn. Now we're going to cut this coil out. Even more increase, but now we're drawing almost an amp from the battery. 12 volts. It's 12 volts all the way across. I love that, man, to have the performance increase directly in your control, like driving a car. It's freaking awesome. So this is a counter rotator, and just give it a second. It's going to kick on, and then it's going to start counter rotating on its own. You can see it start to want to go right now. No help whatsoever. That is amazing. All right, back here we got an amethyst sphere and a fluorite sphere. And right next to that, we got my mechanical switch. This whole thing will run on this. Uh-oh. And it's totally maneuverable. You just have to keep those ends really close to one another, and it'll start bouncing off the copper, and it'll run it at a significant rate of speed too. It's like, that's a good switch. I know it looks kind of ghetto, but we're using a paper clip, which magnetically is very tough. You know, it's very magnetic, but at the same time, it's a very tough metal. And then this is a little bit looser copper. We get no green arcing, and I can turn it all the way up. You get a white spark, though. Yeah, this thing will get all the way going on its one drive, like you've seen it. just now. That's about 1,000 RPMs. Now, what I'm gonna do, I pretty much have it already done. Let's see. Oh man, it's not gonna fit. I need a smaller one. But it's definitely getting a reading off of that from being that far away. It's still working. But I need to make another coil, definitely, for a smaller version of this. Just a smaller bobbin. I'm probably going to put maybe twice as much 32 in there. It's 11,000 turns of 32. And as you can see here, the lights are lighting up, showing that these capacitors are being filled. All right. Let's see what kind of juice we're getting out of this end here. I know on the oscilloscope, it's a straight line. This is straight line DC coming out of the end here. Wow, that's interesting. At the current rate of speed and the distance of the coil, we're getting 12.9 DC volts off of this apparatus right here. That's awesome when it's all kind of synced in like that. 12 volts in, 12 volts out. I'm pretty sure it's like 12.2 now, maybe 12.1. This is 12.9. So, huh. No, I'm not saying anything. I'm just saying that's what my meter says. All right, let's turn on our middle gear. Now it's like, see, same amount of voltage, but our amps went up by 10 times from 60 to 600. And we're getting 27 volts right now. I believe this will continue to increase in voltage to a certain point. $29. See, not only is the coil connected to the scrubber, I like to call it, 30.4 volts. It's also connected to itself via a Schottky diode. So the negative end is facing the positive end and is connected. Positive end's connected to the negative end, like in series. So, from my experience, what's happening here is that the energy is now forced into a loop and gets siphoned off by this apparatus. 31.1. We are balanced at 31.1. Now with this, you're going to get, with bigger magnets, you're going to get a bigger reading. This isn't like SG where you're going to get the same reading pretty much. Whatever you do, you can flip on. Let me get the circuit.
Thanks.
Okay, so what these do is I want to say funnels the input energy directly through the circuit, so it like siphons off, like I said, to run its components, but then the bulk of the energy gets sent through the circuit to whatever you're charging. Or, like this, whenever you're doing 31.3. So that's about the max we're going to get from, it's like 31. So let me turn on the overdrive here. And we'll get in the last little bit. We'll see what the, yeah, it's not going to be that much more. 33.4. I'm going to make a commutator plate specifically for the meter. And I'm going to have a brushes connected to it so I can get some readings off of whatever's going on in here. I've been curious since I built it, like what's going on in there, and you can't really attach a meter to it because then it won't work. 35 volts, and it's all capacitor dump bank stuff. So when you connect this to something that it likes, it goes away instantaneously. 35 volts is gone, and it works like a capacitor does, like not a cap bank, but like a cap. So I want to kind of find out something to connect that to. Should be all right. Connected to something. I keep on hitting the mic, man. I'm gonna put it on the table. Let me know if there's any interference. Yeah. Right. So right now, I don't know, this circuit right here runs this motor with all my switching very well. And that's pretty much what I have to say about it. Runs very well. All right. So I think there's another way to set this up that I can actually use it to run like a light bulb or something, but it isn't this way. Amazing. So I have just a little idea here. I want that to go like sliding. It's being held in place by the wire right now. But anyway, it's spinning this way, right? So we've got north and south. So this is pulling, and then this is north. So this is pushing, pulling, pushing. It's working the way it's supposed to work. And I think it's only beneficial if you have the motor on. But I think it helps like a lot. You just have to have the motor running. "36. That's awesome. So the south goes all the way up to like right around here. So it's kind of like a diamond shape almost, or a conal shape. The south, with all the south facing inward, goes like all the way almost up to the top of the shaft. And the shaft is non-magnetic, or it's magnetic of steel. It's not magnetic, but there's magnetic property, I guess. So yeah, that's awesome. And then let's see how far out the north sticks out. Right about here. That's weird. Might need a battery for this. So right about out here, it's pulsing north. That's all interesting to me. Shove this in the hole here. Wow. Okay, so this is generating north in the middle. Solid north. It's not pulsing. That's awesome. That's I didn't even realize that. That's so cool. So all that pulsing north on the inside here is making this one solid north. Let's see about shoving it in here. North and south. That's sweet. I think it's going to be the same though. That's the magnets. This one right here, because it's got no power going through it, that's coming from the battery. It's got a different reading. Trying to get it close to read that south, and it's just not close enough. But I guess the imprint of the north is all up and down this thing. $1,300. So I was just wondering, like, what I should put on the end of this thing. I'm thinking that it's going to be, if I had a PWM, it would be that. But I blew out my last one trying to get a reading. And I just wasn't thinking. I was tired. And I moved all the wires and I forgot to turn it off. So pop, there it went. But I mean, they cost like 10, 12 bucks. I'm going to get myself another one eventually. Right. Right. One more. All right. And now, and like I said, this is straight DC coming out of here. It's not like it doesn't have a wave to it. And boom, we're down to 0. Oh, I just heard vibration, and what the hell was that? Something outside, I think. All right, so let's hook up multimeter, coil. Huh, it doesn't look like the coil is going to do anything. This is 1500 turns of 32, and it's at 0.04 of a volt. I don't know. That's probably not what you need, like a bulb or something. So I got another idea that will more demonstrate. I got some 12-volt LEDs. Well, looks like I got one right now. I know I got more, but I'm not going to look for them. I got this. This is just a little light, and we'll see what's up. Yeah, that works. Sweet. All right. So we'll hook the multimeter back up to the end of this. Put some juice into it. Yeah, that light lights right up, man. That's awesome. And it flows directly in and out. It's awesome. There's 440 or 4.37 volts coming out of this end with the load on it. That's awesome. Overdrive. Now we can make the overdrive more powerful by moving this clip to right here. Then it's just an 18 gauge strand, about 300 turns with 12 volts going through it. So I don't want to burn my transistor out. That's why I haven't done that yet. All right, so this right here is the result of this coil being close to the rotor, being fed through this scrubber right here, coming out crisp DC on the other end, and that light is bright. It can be a lot brighter though, no doubt. It's only got like 4.5 volts flowing through it. There we go. We backed out the copper a little bit, and we got more voltage. A little bit, but just a little more. 13.8, 1382. Kind of want to move this coil out of the way and move this one like up in there. All right, so this is a pulse motor. It's running on a trigger switch, and it's got, let me think, 5 drive coils that are in increments. I can turn some of them off and some of them on at the flip of a switch. For example, we're collecting magnetic field off of this 32 gauge coil, 11,000 turns. It's feeding this scrubber right here, and what it does is it takes the broken AC, or not the broken AC, but the unusable. That's not even what I mean. It takes the AC electricity in, and it puts scrubbed DC out. So when you read this on a oscilloscope, it's a flat line above the mark. So that's what happens when you put it through this. And when it comes out the other end, voila. Sweet. Now you got to be thinking to yourself, is this one affecting the rotor at all? And the answer is yes. Very much so. Now I did all my amp tests with the power supply before I started the stream. Right now, it's taking about 60 to 100 milliamps to run 12 volts to 60 to 100 milliamps. And now I'll flip the first switch. This is gonna, this cuts out this coil and this coil. So right now it's these two coils and this coil. This is a trifilar coil, so it has a trigger and two other coils inside of it. So 2 coils, 3 coils. That's running right now, and at the end of the third one, we connect the ground, which we just turned on, and it connects to the ground. So these two get eliminated by changing where the ground is. Path of least resistance. It's going to take the first path that it can to the ground, shortest path. Sweet. So simple. Using that to our benefit. Great. All right, so that one's on. I'll turn the power on, the overdrive. This is just these 2 coils now. We're going to eliminate this one. So we change the ground from there to right here. Now, let me see what kind of readings we're getting. Yeah, about 1300. Doesn't seem right though. That's kind of nerve-wracking. Huh. All right, we're good. Move the coil out a little bit more. Now I'm thinking this will be a cool experiment. I'm going to put this coil in between the rotor and this coil, and then I'm going to turn this coil on. Or should I do it over here? I think I should do it on this side, honestly. And then any pulsing energy that we get from the magnetic field of this coil will saturate this coil. And the magnets will be hitting it from the other side. So I think that'll be righteous. Oh man, I'm making that same mistake again. All right, now we're up to 9.2. 9.2. We're all the way up though. So that, look at the light though. And then these have got juice in them. So 9.09, and we've leveled off 9.08. 9.07. We're still slowing down due to the effect that I was discussing that the copper has on the magnets in the rotor. Definitely there's a drag on the rotor. Aluminum, copper, any of that. On the magnets, there's a drag because there's a magnetic principle that is being applied that is not directly magnetic. It means that I can put an aluminum disc next to this magnet, nothing will happen. But if I move that magnet quickly past the aluminum disc, it'll move the aluminum disc. It'll move a copper disc too. It'll move metal without actually being magnetically attracted to it or repel from it. I think that has to do with the eddy currents. I'm not exactly sure, because I know that when you have either your aluminum disc stationary or your magnetic disc stationary and the other one spinning, you get more eddy currents than if they're both spinning, unless they're counter rotating. Because then you get way more of the eddy currents than you would either of the other ways. But you know what? I think it's awesome. So that's it with all the power running through it because of that disc right there. I'll put a bearing on there for good measure because we're just spinning it right now. And I'll put my, yeah, man, for a gravity flyer, I was wondering if I could use one of these 1/4-inch aluminum discs for it. Don't know if it's even the right type of, or maybe it's too thick. I don't know. I don't know anything about it, but I got questions. So this is adding more load onto the rotor. We've dropped now to 8.93 volts. Heck yeah. This is awesome. All right, so the aluminum disc is spinning due to magnetism, due to a grip. Now, if I do this, now we're getting major eddies off of this. Like, I can, and then, if you put a contact in the middle and a contact on the edge, there's your Faraday disc. The way I wanted to build it, stationary like so, and have the magnet spinning on the bottom and on the top, and have your contacts right here, like in the middle, and then on the edge. And then you can either do that, or you can spin the aluminum disc and keep the other rotor steady. And after what I just seen today, that would be awesome. Like to get a reading on that. Like and I understand, like, nah, man, oh God, wow. That would be so freaking awesome to and I saw the oscilloscope reading. It's pretty freaking cool, man. That's awesome. I just I was talking with Chad and a few other people about eddy currents, and yeah, bolt that bottom disc down so that it doesn't spin, and then I'm pretty sure with the power you got coursing through that top disc, it's going to create a lot of eddy current. And what do you got, like 8 or 10 magnets on the bottom one? Oh my God, dude. But I don't know. It's your stuff, man. I love this kind of rotating pulse motor. 3 magnets on the top, cubes. Underneath the hood, we've got 3 wedge-shaped magnets. We got 3 batteries. 2 of them are hooked up currently. We got 1 transistor from Toshiba. Trigger coil right here. I got 2 resistors on the trigger coil. I think I'm going to move one of those resistors, 32 gauge drive coil, so that we don't continuously burn out transistors when trying to run 2. Right now, I believe it's the 20 gauge strand that is running. Let me look real quick. Bottom one is what we got. Yeah, the bottom one is the 20 gauge. So if we hook the 32 gauge up and it stops blowing transistors, this will perform a lot better than you just seen it perform. The performance will go up. Those batteries will die a little bit quicker. .88. Wow, dude. What a way to turn it on. What a number to see when you turn on your multimeter. 888. So cool. Now it's 887, but I saw it. I had the moment. So you can't see that number on a clock. It doesn't happen in time. You get 888 on a multimeter. So I'm going to see if we can run. This will run with all this load on it, on its most efficient part, where this is the least performance. We're going to see if it stopped already. It's already stopped. So we'll remove one load. That's this. So we need to be able to put more voltage into it for the most efficient way for it to work right. But we'll turn on the next one. And there, that's got enough torque to overcome this load, which is quite a bit on the rotor with it being that close and with it being shorted out with the diode. That's quite a pull on the rotor. So I'm thinking about maybe putting some caps in this mix, some capacitors. All right. Man, man, this is so cool being able to like stay within a certain parameter and have it all work like anyway, except for, you know, just the one instance with the two loads, it stopped altogether. But with 12 volts as being your input and not being able to manipulate that at all, because I don't have a speed dial, all I have is switches. It's all 12 volts and it all works. So, you know, a lot of my live streams, I've had instances where I would try things and they wouldn't work. And that's, in my mind, that's okay. I mean, that is not the end of the world. And you learn. You're supposed to learn, especially like when your stuff is all out there. You need to turn the power off before you start moving it around. 8.27, 0.28. That's awesome. Here, now let's pick that up and see what happens here. Went up a little bit. So this is definitely a load right here. It's like not a huge load on it because it's so high, but it's definitely slowing it down. Even though it's moving, it's still slowing it down. Move the big load out. Oh my God, look at that. Um, yeah, I feel like now we got wires crossed. I'm gonna move that. Coil. Yay, I remembered to turn the power off this time. Now, what I think will be able to reduce the load that that coil has on the rotor is to take that diode out of there. That's what I'm going to do. All right. Now, the next time that goes into play, I doubt it will have such an effect. Okay, where's my little thing? Over there. I'm going to see if it being that far away has the effect I desire. I'm just trying to touch the fringe. That can't be right though. It's kind of what I want right there. I just touched it. Over one hump, and we got 3 out of that. Okay. It's 2 humps. Exactly what I want. All right, that's going to help out a lot. A lot. Mark my words, I said help out. As long as there's juice flowing through it, that should help out a lot. Oh, it's about the equal amount. Definitely a load, but not as bad, I don't think. Maybe equal. So if I had 24 volts, I bet the extended circuit would work the best. But I only got 12 that I'm going to work with right now, because when I cut it down to this little one, 24 volts is going to burn everything. So right now, currently, we've got these 2 coils and this coil on. And this coil is pulsing into this coil, generating, I'm thinking, I don't know how many volts. and then it's getting the action from the rotor. So it's at 13.65. 13.65 on this little light right here. 12 volts. 14. So each time you hear the click, I am demonstrating a power increase or decrease, a performance increase or decrease. And the same with the efficiency. As the performance goes up, the efficiency usually goes up. Or the other way around. What I'm trying to say is when the amp draw goes down, the speed goes down. So right now it's at about 900. Now it's at 600. We're just going to let it cool off a little bit, and then we're going to throw the last one. And it'll go down to 60 milliamps. And I think it'll stop. We'll see what happens. I think it's going to stop with that big blue coil on it like that. If we had 24 volts, it'd be awesome right now. It'd be fast. It'd be drawing about 300 or 400 milliamps. All right. Might need some glue on that. Looks like it's going to work. Heck yeah. There's a slight vibration. That center hole might be a little off on my new rotor, like a half a millimeter off. All right. See, really all I'm doing is demonstrating how these things work, that they do work. And if you'd love to have, like, do something for fun, building one that works is quite satisfying. Especially the counter rotators, they're fun. Wow, look at that, all lit up. We're not getting as much drag on the rotor either. So we'll flip this one on, we'll flip this one back off. We'll step down to that one. I mean, after me explaining it, so many times, it's all good. I'll keep explaining it. There's nothing different than what I'm explaining, though. It's like, this is all drive. The blue coil is generating electricity for this light and then some. 13.6 volts of DC scrubbed electricity coming flatlined out the other side. And it does it all for me. That's awesome. We got a stack of permanent magnet toroids right here, attracting the rotor. Attract. These ones over here are repelling. So they're pushing. So you get how that works? That's awesome. And that does work. You just need to have your motor running. It doesn't do it on its own. It never will. There's no cusp. Because once you touch that cusp, you will fall to the other side. There is no thing that you can sit on and watch it happen. It's all hard work. And when you figure this out for yourself, you'll be satisfied with just having it help other than run it all on its own. And I'm just talking about this design won't do that. I don't know about any, more exotic permanent magnet designs, but I'm pretty sure that this one will help the rotation, not rotate it on its own. Because you saw me when I did the rotation check, right? All right, so a rotation check goes like this. So we got like 4 out of that. No. About 5 to 6 rotations on one hump. So what I mean by a hump is when you get to the point where you get to what you think is going to be the cusp, right? The part that you're going to sit on, and then you let it go. And if you just let it go on one hump, you're probably only going to get one hump. But if you go the next hump, like so, you get 5 or, that was like 3 or 4. But if you go 2 humps, you'll get. So if you move 2 magnets with momentum past the hump, you'll get 3 to 4 rotations easy. And that is obviously going to help when you turn the motor on. It's going to push and pull this thing, but it's only going to, help a little bit. It's only going to help a little bit. And you got to get those magnets in the right spot. It's called fringe. It's got to be on the fringe. The edge of these magnets, you got to touch the edge of those magnets. You can't really have those fields interacting too much or you're going to get lots of drag. Then it goes this way. Now, I want to build a Tesla coil so I can resonate frequency effectively. I have this quartz crystal. As you can see, the Merkaba, the center of the Star of David, like where they come together, it's a hexagonal shape of the cup and the blade. They come together. So what I want to do with this is I want to wrap it in copper. I want to put it in water. And then I want to resonate that water. I want to structure that water around the crystal and the copper. And I want to transmutate the copper into the crystal, or the crystal into the copper. But I think it's going to go copper into crystal because of the composition. If it happens at all, you know, transmutation, that's what that is. And part of it will rub off onto this. So we're not necessarily, we're definitely changing the composition, but we are not, it's not like I'm turning the quartz into copper. I'm turning it into something else. And the same with iron infused plants. This is another theory that I have. If we can grow the plant in the resonance, it'll open up enough to receive other molecules than just what it needs for nourishment. And yeah, I think this is how some of our more exotic things were created, like frankincense. That is definitely a transmutated thing. That is not just from a plant. That is also a plant that has absorbed something else. So in other words, it wasn't quote unquote natural, even though it happened in a natural phenomenon. Yeah, I guess it was natural then. You know, it is natural. This stuff can occur on a natural basis and probably does all the time. The transmutation type thing, you know, like algae in a pond or rust. If you get a little bit of rust in that pool of water, eventually you're going to have a lot of rust. It's not the same thing, but it, you know, kind of. And then the frequency thing, how you can like touch whatever and it will adopt the frequency or be structured to the frequency that you touched it with. Whether it's you touching it with the frequency or the frequency is touching it with the frequency is what's changing the frequency. And then like gray matter or the ooze, movies like this is what I think of when I think of that. It's like, oh my God, it's touching me and I'm turning into it. You know, the whole universe would be the same eventually. But I now multiple frequencies, I exert multiple frequencies. You know, like the souls, they have, you know, more light guided frequencies, very high level, like photon frequencies. When we think of a soul, we think of a color of light. That's what we think of inherently because of pictures we've seen, things we've been taught. And yeah, if you want to break it down like that, that's cool. Then that would mean that black is the eldest and the most wise would be all the colors mixed together, which would be black. White is an absence of color. And then next would come violet or, you know, purple, like so. But there's definitely a hierarchy of both white and black, definitely. And the black is the wiser one. Black is the wiser one. I feel like there's like a like a dream state almost that occurs when we talk about good and evil. It's like it's upside down and backwards because I don't know, man. It's just I don't get it. And I don't believe that any of what we know to be true about good and evil is truth at all. And short of dropping names, I just think that there's a gross misunderstanding that needs to be overcome. And the pyramids, man, wow, yeah. Like, it's definitely a large scale Tesla recreated a pyramid. What he was trying to do. But like two basically miles down. He didn't have anything like that. 2 kilometers down, there's like stuff happening below the pyramids. 2 kilometers down, dude. And I say no. It was a great attempt, but like everybody, we are limited by our time currently, like the time period that we're in. I think we have great advantages in the time period that we're in. So I mean, for sure. And stuff like this, like, it's fun, man. It's people love to watch things spin. People like things that spin. People don't like building things that spin because you got to balance that thing so that it spins appropriately, so that it doesn't wobble everything. So that, yeah, it's a little bit of a hard thing to do, but eventually you'll get one or two rotors that make sense. um, like this one is, I don't know. I don't really have anything bad to say about it. I tried doing a 1/2 inch in millimeters so that I could get a 1/2 inch hole through the center there, and it just came out the hole's a little bit too small, so I can't even fit the rod in there. 12.8 millimeters, not big enough. So if I went 12.9, it probably would have worked. And then we'd be looking at something totally different. But I'll definitely give it another go. I got to get more filament. I need iron infused PLA and carbon fiber filament, and then I'll make another one. It'll be sweet. All right, well, this is pretty cool. See, and now that we've got the light in, connected to this, maybe we can hook something else up to that light in series and then connect it back to the thing right here. I don't know. I'm just trying to figure out the uses for this thing. And right now I can light a light bulb. Seems like a lot of stuff to just light a light bulb. So I'm going to look farther and deeper into this. It looks like there's even, there's 2 ways to hook it up too. So I think you can hook this up as like a power source or an in-series cap bank. Right now we got this light with 13 volts going through it. 13.7. Turn on the overdrive. Now it only goes like 200 more RPMs, but we get, looks like yeah, like 700.7 amp volts. Sorry, 14.1 altogether. So I had the diode hooked up a certain way. I'm thinking maybe if I just flip it around, we'll get a different. I think this is right. Oh yeah, that is way better. Like less load, better. But we are only making 7.8 volts. I think that's because the energy is now flowing back into the coil the way it should be. Or at least some of it is. Wow, that's so much better. Yeah. All right, so what I did here is I flipped the diode to be parallel with the coil. We're still getting about 7.7 volts. Our light is lit. We got our light. So there's some in the bank here and there's some that's coming out. So we can actually hook up more stuff to this at the current speed and it'll work. So 8, right where it is, we got 8. I think we're going to stay at around 8, might go 7.9, but 8 volts. That's lighting this light coming out the scrubbed end of this cap bank. I think that's pretty good. That's like 12 volts for the light. Well, I don't even know exactly how to break it down. The light is lit, not as bright as it can be. And then there's 8. And this is all because I switched the diode. .1 right up next to it. All right, so I'm going to get a reading on the battery because I'm just trying to wear the batteries down a little bit so that I can use them as charge batteries without anything bad happening. What's up?
That was 9 minutes.
Yeah, been pretty good. All right. Right, we are at 12.4, 12.43 and climbing. I think that means it's taking the juice from the multimeter. Yeah, I'm gonna get the other battery just for a second. We're gonna run the extended drive with a 24 volt input. Not what I think. Just make sure that's off. Make sure that's off. Good. My light is extremely bright. This is 24 volts in. We're not going to be throwing any switches with this, but yeah. See, that's beautiful right there. And that's only pulling about 300 or 400 milliamps at 24 volts. Yeah, it really feels like that on that partial millimeter. It's a little off in the center. You can tell by the vibration in the table. All right. But, you know, it's a work in progress. And I'm using Tinkercad, so maybe I'm not good enough to use Tinkercad. You need an additional set of skills to use Tinkercad than you do to use, you know, a program that does all that stuff for you. I'd love to learn how to do all that other stuff though, so that it'll do it for me. I really do. I wish it was just easier to learn. Wish I learned some more of that in college than I did. And it's not like I didn't learn it. You know, I didn't learn it because I didn't take it. I have an accounting degree. I'm an accountant. How's it going? You good? That's good. Who wants to see a different rotor? This is my latest and greatest. But we can watch a different one spin for a minute. All right. Stop that so I can focus real quick. We're going to use the same coil spread. We're just going to hook up a much larger rotor with bigger magnets. I love that one though. It's so crisp. Very nice. I will return in a moment. All right, we are almost ready. I wonder, this is a 9-magnet rotor. I can't really have this spread on a single series. Huh. I want this one though. Maybe I'll move the coils around real quick. That glue dried up on that. It's pretty bad. We're going to go with the painted side. Nice and smooth. All right, so we're going to take this one out. Can't really tell where the magnets are. There we go. All right, I think that'll work. Hopefully it's that simple. Gotta get this up. Put it right here. It's off. That's off. We'll worry about that in a second. Here we go. That's running smooth. Woo. Yeah. It's a little bit more off balance than the other one, but once it gets spinning, I think we'll be all right. One of the magnets I need to fix. All right, here, let's try it. So neat. Boom. Right. So what I want to do with my Tesla coil is I want to get it to resonate. And then I want to wrap this in copper, like 3 layers of copper, just copper for the mineral. And I want to put it in water. And I want to use my Tesla coil to structure that water around the crystal and the copper. All in attempt to transmute some copper into the quartz. I'm trying to bridge a gap that is definitely there. And that has become a goal of mine, to bridge the gap between hot and cold, and so that they can be utilized at the same time. You don't just scrap one and pick up another. You got to make them both work at the same time, and then you will get what you want, the desired effect. Just sandbagging stuff, I don't see the point, really. Oh, that's so satisfying. This rotor bit the big one when the magnet flew out, and I put it back in, and I taped it. And the tape has been working very well thus far. I haven't done anything outrageous with it. And so you got a slight vibration in this pole right here. So that means it's a little bit off balance. I think it's that one magnet that kind of is loose in there. But I'm going to glue it down, and it's going to be all right after that, because the tape's going to hold it in place. I didn't have tape on it before, so it was just magnets sticking out. And they weren't sticking out. They were totally embedded in the rotor. But as for the force, they were sticking out. Because one of them flew right out of there going about 1,500 RPMs, man. And it's not this or this that was destructive. It was the way that I built it. That, and me, I'm just straight off the street, no education about this whatsoever. I taught myself how to balance the stuff to the best of my abilities using Tinkercad. Now, I know that the other programs are a lot better at balancing stuff, but the learning curve on those programs requires, a lot of reading, or at least an education. Definitely a lot of reading. And if you don't know what that means, so man, learning new software is difficult. So for those of you that it comes easy to, don't go around saying that it's easy, because it's not. It takes a lot of work. You just aren't aware of the amount of work you're putting into it. And that's okay. There's a lot of drugs out there that make time just melt away. Ritalin is one of those drugs. Okay? You will be focused so intently on what you're doing that time will not be a factor. You could spend hours and days just doing it until it's done. And people will worry about you. They do. They worry. Well, they're worried about me. That's for sure. Like, you're not sleeping. You're not eating. No, I'm deciphering the binary code. That's what I'm doing. And in order to decipher any binary code, you need a legend. You need there to be A equals 000111011. That's what A equals, because A equals 99. You plug 99 into your rubric, and you'll get the binary sequence for 99, which is equivalent to either a period or the A in the alphabet. And it's all kind of linked together like that. But it's all man-made. All of it's man-made. Binary is not man-made, but the binary sequence, that the legend, is man-made, not the sequence. I'm not trying to say that the binary rubric that's mathematical. Well, I guess it is man-made. It's mathematical. Anyway, man, I did that all in a night. I made copies of it, and I gave it to all my classmates the next day. I'm like, here, this is how you do this. Oh man, it must have seemed like such a I'm not gonna say the word, but you know what I mean. Know it all, kind of, but worse than that. It was no big deal. And those who know about the ACSII code know that it's really easy to do. SCS, ACSII. See, because as soon as you know how to plug it in, start with your 256, 128, yada, yada, yada. It's almost like Minesweep. How it works out, man. It's awesome. Yeah, I beat my first Minesweep when I was 6. No, I'm kidding. I was 10. That was fun, man. Minesweep is a great game. All right, so Hear that drag? Wow. But the lights, oh my God. I bet you I could light up a whole string of these LEDs, man. Just light up this whole table with LEDs just off of this one coil. Be fun, but I can't find any more LEDs right now. I'm constantly cleaning and rooting things out. What's the next project going to be about? Yeah, until I get a good source of data, I'm not going to do anything exotic. Because I know I was reaching out to different channels for information on how to do this stuff, and I'm coming up dry. At least I can't get a hold of the main content creators. I haven't really tried, actually. And apparently, I guess some of them don't appreciate pulse motors. That's okay. I don't mind. I do. Keeps my head centered, focused. I know it doesn't look very focused, but I know where everything is on this table and what it does. See, that didn't sound right. That sounded wrong. Yeah. Well, I don't have anything to complain about really today. That's awesome. Today's a good day. Bring it on, man. I feel like I can take on anybody who's got anything to say. Seriously, it's like feels so good. And it doesn't always have to be like it usually is. So that's where I'm at. It doesn't have to be all opposed to me. And it's like the opposition won't take a direct approach. It's like dealing with narcissism. It's so like it's convoluted. They're talking about you, and everything that they're saying about you is virtually not in your favor, but it doesn't bother you. It's like you know who you are, you know what you've done, and everything else is a lie. It's just straight up not true. Because an opinion about you without any information to back it up is a lie. And that happens a lot. Now, if you got like solid, concrete information, you know, I'm willing to listen to people. If I'm doing something that's offending you or insulting you, I apologize. Sincerely. I don't mean to do that to anybody. Here's a speedometer, little speed dial. This might be a pot too. Yeah, this is a pot. But you can use a pot to govern speed. I can do that. So it'll be right here next to the battery. I'll plug in the wire to the power, and then the output to this, and then I can control the voltage, and I'll run with 24. Heck yeah, that'll be fun. And that light will stay lit as long as the rotor's spinning, pretty much. So that's after the effect of turning it off. You turn it off and you still get electricity coming out of it, which is a residual effect, but it's awesome. That is awesome. Get power without power is awesome, even if it's a little bit. So, I mean, thank you all. Really appreciate people coming by and watching this. It is kind of old school. I do want to experiment, like I said, with Tesla coils. I have owned a Tesla coil. I bought it off the market, though. I didn't build it myself. And it had some awesome effects that went along with it. Just simple lighting effects, but very cool. Now, see, if transmutation is a thing, like a real thing, then I should be able to transmutate copper into this quartz and vice versa. Simply by getting them in close proximity, putting them in something you can structure with the resonance, water, of course. Then everything kind of gets structured into the same structure. You know, we call it a honeycomb, hexagonal structure. And it should combine at least a little bit. Resonate the water with this wrapped in copper in it and see if we get any, you know, copper quartz. I mean, why shouldn't it work that way if it works at all? I think it works. I wouldn't even be thinking about like trying to do something like that. I would definitely stay away from it, thinking that it wouldn't work. But I think, and especially like plants and living things in the resonance, if it truly opens up the plant so that it will receive more nutrients at once, you know, like make its veins expand a little bit, then you can get other molecules in there that they couldn't before. So you can put metal in there. You can put, you know, metal's the big one. You can have plants that'll grow with metal in them. You're well on your way to making frankincense. And I would say, I don't know, maybe more like a pine cone. It's like a seed, a fruit. Fruit, that's what it is. but it's not edible fruit. Because I believe it's derived from a plant, much like a pine tree or a Joshua tree. And then myrrh, like that stuff is more prevalent. It's like oil. At least that's how I get myrrh, is in oil form. And it reminds me much of like tea tree oil. See, I'm doing that with my finger. Get my light bulbs out here. I'll be able to turn on all these big lights too with just my finger using this. Because all this stuff is coming into play, like being able to grow plants faster. Yeah, all this is great. And I think it's all coming into play with a greater understanding of what the material that we already have. And yeah, pick my brain. Go right ahead, man. I don't have the money to freaking do this. And it's going to cost. It's going to cost some money. I mean, making my Tesla coil is probably going to cost me $300 if I get everything right the first time. Hmm? $300. That's what I'm guessing. It might cost more. So that's off of this. And as long as that's spinning, that'll be lit. The magnets in here are very strong. And all of this is coming off the induction, magnetic induction on this coil. All the heat that's being generated off of this being filtered through this machine and turned into a light. It's like a cap bank, but it's got capacitors and rectifiers on it. But who wants to like do that? Who wants to spin this thing with their hand like every 15 seconds? Who wants to do that? Let's spin it this way. Because that's the way the diodes are facing. So I'm thinking that this way we're going to get a little bit better rotation than the other way. But wait a minute. If we go by this design, if we spin it this way, that's going to spin that way. So we want to spin it that way. And now essentially it's a counter rotator. Even though the stator isn't moving, all the diodes are facing that way. I bet we'll get a lot more rotation on this going this way. Yeah, it's not much, but you can definitely tell there's a little bit more torque this way. I love this circuit. Simple, man. Transistor, one connection to the base, to the trigger, one connection from the collector to the power, one connection from the collector to the light, one connection from the emitter to the coil, one connection from the trigger to the emitter, and then one connection to the light. That's actually 7. And then the ground, of course. 8 connections. But if we just look at what's connected to the transistor itself, we've got 1 for the base, 2 for the collector, and 3 for the emitter. That's what's connected to the transistor. So I call it the 1, 2, 3. It has 6 connections in total. 1 plus 2 plus 3. Right on. And it doesn't have that squeak that the SG has. And it probably doesn't go as fast as the SG either. But yeah, man, it runs things very smoothly. And I'd say that that sound is crisp. It's not like, I don't know. There's some pros and cons. Let me put it that way. SG, much better generator than this circuit, although I can clip something to the collector of this and then run that with that connection alone. That yeah, I might do that in the next time. Like connect another rotor and have it moving somewhere else on the board here. Thank you very much, ladies and gentlemen. It's been a blast. Thanks for hanging out. We'll wrap it up here in the next 10 minutes. I really want to get doing that though. And if somebody else does this thing with the copper and the transmutation, yeah, go for it, man. I really, and the plants and the iron mineral, go for that too. Let me get so put it in resonance, a plant, and then like make a soil mixture or a hydro mixture, whatever you're growing your plants with. Put this iron in there. And as far as I know, there's already like dirt in this, so just mix it straight in with the soil, probably 1 to 5. 1 part iron, 5 parts soil, and then get it in resonance and see what happens. And like, yeah, like the fantastic stuff that isn't around anymore that we know existed, like not just but 2,000 years ago, 2,500 years ago, 10,000 years ago. It's we need to recreate it now. I'm talking like that electrified plant. You know what I'm saying? That plant with the energy just coursing through it. And yeah, I don't think you use AC or DC to reach that state. But once you have iron infused into your plant or the copper infused into your crystal, then you're starting to bridge gaps. You're starting to make bridges. And I think that's where our problem is currently. I mean, there's lots of stuff going on the cold side. I'm keeping it up on the hot side. Um, yeah, there's lots of things I need to learn though, man. And a lot of it doesn't have anything to do with pulse motors or electricity in order to get where I want to go. Uh, yeah, it's how to, if you want to say something negative, you have to sit on that virtually forever. You never let that out, and you don't let it stew in you either. You have to just let it go. The negativity, just let it go. You don't have to fight that. You don't have to have a rebuttal for something everybody says to you. That's what I got to keep telling myself. You don't have to fight all the time. Just let it go, man. Let it be. That's what it is, and that's what it is. Just let it lie. You don't have to engage with that. I'm really not a negative person. I mean, some people may have derived the opinion that, yeah, this guy's a real dick. But yeah, I'm not. I'm really not. I just don't like being accosted open endedly, like, narcissists would do it. And then everything you say makes the situation worse because there's no true target for what you're doing. And so it just makes you look worse and worse and worse. And so the only way to stop that from happening is to let it go. And let go of everybody that's embraced in that. I call it child's play. There's the movie, it's like it's very bad. Naughty little children. Chucky had a cousin, Charles. That's moving really smoothly. Very cool. So, I mean, I feel like I'm getting a better grip on things in my life, in my channel. Keeping it simple. I'm not trying to do so much that I just break everything. No, we're not trying to do that. Right now, I got two things. My counter rotating pulse motor. Top goes that way. Or no, bottom goes that way, top goes that way. And it works. Awesome. That's cool. All right. So this is the 3 ground system. Right now, all 3 coils are hooked up, or all 4, I should say. There's 2 in here. Trifilar coil. All right, I've shut this one off now. And now for a brief moment, I'll shut this one off. So I don't know. I think this one's actually better now than just this one alone. It's pretty comparable, comparable. This one's a little faster. So when I turn the switch on, what it does is it activates the connection to the ground. Instead of turning off this coil, I'm turning on that connection, which then turns this coil off. Path of least resistance. Really neat. Thank you very much, everybody. Appreciate you. Have a great night. Please subscribe. Bye now.